Okay, this will start Chapter 7 on graphing exponential functions and solving exponential equations. We're going to do the exponential first, and then 7.3 and 7.4 we'll actually get into the logarithms. Okay, and I'm kind of combining these two sections into one. First, the author talks about an exponential function. First, if it tells you it's a function, you know it passes the vertical line test for a graph. An exponential function in general is an equation of the form y equals a b to the x power, where a does not equal 0, b is greater than 0, so your b value is positive, and b does not equal 1. So, example, if they say to graph the exponential function y equals 2 to the x power. Okay, so on your calculator, so go to the y equals and put in 2, and then use the caret, the up arrow, caret, and use the xt theta n key. So you have y equals 2 to the x power. And I'm going to do zoom. And if you go down to zoom 0, zoom fit will always give you a graph. Okay, the calculator picks the window. So do zoom 0 and let it graph. Okay, and it should give you something like this, where the graph is going something like this, and then it will go up exponentially. Okay, what is this point right here? Okay, do second function calculate right above the trace key, and do value. Second function calculate right above the trace key and do value at x equals, and if I'm right on the
0.
axis, x is 0, and what's the y value? 1. So this ordered pair is 0, 1. And check, if you put y equals 2 to the 0 power, what's anything to the 0 power? 2 to the 0 power is 1. Anything to the 0 power is 1. The only exception is 0 to the 0 power is undefined. So that's why that ordered pair, if the x is 0, the y is 1. Okay? Okay, try another one. If you have another example, say you have y equals 1/2 to the x power. Okay, so we can clear that, and you can either put in 1 divided by 2, or you can put in 0.5 and raise it to the x power, 1/2 to the x power. And I'm still going to do zoom 0. Zoom fit will at least give you a starting point on your graph. Okay. Okay, and you should still have something like this. Okay. Check. If you do second function calculate value at x equals 0, still goes through at 0, 1. Okay? So if it's a number, if this is a number, okay, larger than 1, you're going to have a graph that looks like this, and it goes up exponentially, goes up rapidly. And this one, if it's a fraction, it's going to go down. Okay? Okay? Okay, with that in mind, we have exponential growth, and those of you that are going on into the sciences, Exponential growth is if A is greater than 0 and B is greater than 1. Okay? And you're graphing y equals a b to the x power. So look at the a in our formula and the b. In this case, it's understood that there'd be a 1 in front of that 2, right? The b would be 2. Okay? If you do exponential growth, and then you can also have exponential decay. And we're going to do some examples with that. And that's if a is greater than 0 and the b is less than 1 and greater than 0. So that's like this example where b is a fraction like 1/2. And you're still graphing the same y equals a b to the x power. So this one is like this example. This one is like this example. So the growth would be where it's going exponentially up, the decay where it's coming back down. In the sciences, like there are examples like for the growth of bacteria, the radioactive substances like the half-lives. There's things to do with exponential growth and decay with electricity, with temperatures, with credit payments. Those, just to name a few. Okay. Now, if you do exponential growth and decay over regular intervals, okay, and it's the same percentage of increase, okay, then there's a formula for that. So when a quantity grows by a fixed percent at regular intervals, the pattern can be represented by there's two possibilities. The growth for exponential growth is y equals a times the quantity 1 plus r and to the t power. And on the calculator, we're going to change that t to an x. The a is the initial amount. The initial amount that you start with before you're measuring the growth or decay. The R is the rate or your percent, and you'll change it to a decimal. The T is the time in intervals, regular intervals. Okay, in this one is growth. Okay, now for a little separator there. For decay, it's y equals a times the quantity. And here's the difference. Decay, it's going to be 1 minus r to the t power. So decay is going to have a minus sign. Okay, now I want to go through a couple of examples. Okay. In 1985, there were 285 cell phones in the town of Centerville. The number of subscribers increased by 75%. Per year, after 1985? How many subscribers or cell phone users? How many subscribers were there in 1994? And that's assuming they go at the same rate. Okay? The number of subscribers increased by 75% per year. So it's going up, so that's growth. Okay, so write the formula down first. Y equals A times the quantity 1 plus R, and then times T. We started with the initial amount was 285, right? The rate, we're going to change that rate, 75%. You're going to drop that percent, yeah, and move the decimal back 2 places. So 0.75 and the T. Now, for the time, we're going to do this by a graph. So we're going to actually put in an X. So on your calculator, clear out that other equation and put in 285 and then times the quantity. And you could go ahead and add those 1.75, or you can put in you can put 1 plus 0.75 too, and raise it. And instead of using T, we're going to change it to an X on the calculator. So 285 times the quantity 1.75, and raise that to the X power. Now look at the years from 1994 to 1985. How many years? 9. Okay, so we're going to go ahead and let the calculator do it, and then we've got to choose a better window. So do zoom 0 to get a graph. Zoom 0.
Takes a long time to find
Think all the calculations this thing's going through. And notice at the end how it goes up rapidly. Okay, now look at the window. If I tried to, I guess I should do this with you. Do second function calculate value, and we want the value in 9 years, right? And it should give us an error. Okay. The reason it gives us an error.
Why didn't you get an error? Why didn't give me an error?
I didn't.
Okay, then your window is different than mine. Okay. If you do get one where it gives you an error, it's because my 9 is not in my window. Go to your window. Go to window.
Window.
What's your X values?
-10 and 10.
Okay. Okay, so yours is different. So, like if I change this to 10 and graph it. Okay, and now do second function calculate value at X equals 9. Second function calculate value at 9. Okay, so if it goes from 285 and every year increases by 75%, 9 years later it grew from 285 subscribers to 43,871. And you have to ignore the point. You're not going to have a fractional part of a subscriber. Okay, so put a graph, and it's going to go up exponentially. This point is still 0, 1, and at over here at 9. So we did 9 and 43,871. So how many were there? That's your answer, 43,871. Okay? Everybody good with that answer?
So we don't mess with 2986.
No, because you're not going to have part of a subscriber. Okay? Okay. The other thing you might put down, because I didn't write it down yet, we did zoom 0. Zoom 0 on the calculator is zoom. It's actually zoom. You do zoom and go down to 0. It's actually zoom fit. So to get the graph, we did zoom fit, which is like zoom 0. That way the calculator, and if you ever get an error when you do second function calculate value, it's because your window's not big enough. Okay? Okay, another example. And I'm not going to write all this down. One of the most common examples of exponential growth deals with bacteria. Okay? And on this one, bacteria can multiply at an alarming rate. Okay? And on this one, the bacteria are actually doubling. Okay? So on this one, we're going to start with 1 bacteria, and we're going to double every hour. By the end of the day, how many bacteria will there be? Okay, so the beginning equation is still y equals a, and this is growth. Y equals a times the quantity 1 plus r to the t power. We're starting with 1 bacteria. And then 1, but if it doubles every hour, that's 100% growth. Okay? So this would be 100%. If you take 100% and drop that and move it back, this is also 1. That's like 1.00. And then to the t power. So this is like 1 times 2 to the t power, or y equals 2 to the t power. In our case, we're going to do 2 to the x power on the calculator. So clear out that equation, do y equals 2, and raise it to the x power. And do zoom fit, zoom 0. Okay, and you see how it stays pretty steady and then exponential growth. Okay? Okay, so look at your window. How many hours in a day?
24.
24. Did your calculator, what's your window on yours?
10.
Okay, so now try your second function calculate value at x equal 24 hours. Should give you an error. Right? Because 24 is not on the screen, right? So we've got to get we got to go bigger than 24. So I'm going to go 30. Okay, and then graph it. Okay, and you see you end up with, it's going to go pretty steady through here and then rapid growth. So at 24 hours, this is still 0, 1. At 24 hours, second function calculate value at x equals 24. Yeah, so in a 24-hour period, okay, up to 16 million bacteria. Do you understand why some people with certain diseases and things can get really sick rapidly? Okay. On these, and you could extend this to, say several days and several months. At a certain point, it says that in reality, exponential growth does not continue indefinitely. There would eventually become a time when there would no longer be room for the bacteria or nutrients to sustain them. Okay, so those are 2 examples of exponential growth. Now let's do one with exponential decay. Okay. Each year, the local country club sponsors a tennis tournament. That should not have an apostrophe. Sorry. Sponsors a tennis tournament. Play starts with 128 players. During each round, play starts with 128 players. During each round, half of the players are eliminated. How many players? Remain after 5 rounds. And you could actually probably just do the arithmetic on this one, but I'm going to give you the idea. Okay, so on this same formula, y equals, except now it's a minus sign. It's 1 minus r to the t power. The initial amount is 128 minus 50%. You're losing 50% or 0.5, right? So y equals 128 times 0.5 to the t power. Okay? So on your calculators, put in y equals 128 and then times 0.5 and raise that to the, we're going to go to the x power. And zoom 0, zoom fit will give you a graph. Okay, and we're only going like 5 rounds, so let's go maybe 8, negative 5 to 8. Whoop, 38, sorry. Let's go to 8. And if you want to see the axis, the y-min, you can change that to a negative number. So you can see part of the axis. Okay, now do second function. Calculate value at x equals, they want after 5 rounds. After 5 rounds, if you look on this one, it's exponential decay. It's going down. Yeah. So after 5 rounds, and it goes to, there were 4 people left, right?
Yep.
So if x is 4, y is, or if x is 5, y is 4. So there's 4 people left. And then if you did second function calculate value at 6, you're down to 2. Second function calculate value at 7, you're down to the winner. So it's going to take 7 rounds for that.
Why did mine do that? I changed my agenda to 7.
Okay, so you should end up with 4. Okay, 4 players left after 5 rounds. Okay, one more exponential decay. Okay, and this one, I'm not going to write all this down. You don't have to write it all down. But this is about the pesticide DDT. This was widely used in the United States until 1992. It is a banned pesticide, okay, because of its toxicity. But on DDT, they have calculated, and those of you that go on into chemistry, they have calculated the half-life to be about 15 years. Okay, so basically, when it's on the ground, okay, if you started with 10 grams of DDT, it would take 15 years to get to 5 grams, 30 years to get to 2.5. Okay, so you understand when they're talking pesticide use, you know, that's a critical factor. Okay, so they think the half-life is equal to about 15 years. So when we're looking at this graph, they're going to say one interval stands for 15 years. Okay, so on this one, they start with 100 grams. And how much is left after 90 years, or basically 6 intervals or cycles. Okay, so still decay. Okay, so y equals a times the quantity 1 minus r to the t power. They're starting with 100. Okay, and you're doing the half-life, which is similar to what we just did on the, so it would be 1 minus 0.5, so 0.5 to the t power. So y equals 100 and 0.5 to the t power, or x on your calculator.
So after 15 years, there would be 50 left?
50, yep. Okay, so let's put that in. It'd be 100 and then 0.5. Do you notice I'm not having to put in the time sign? Yeah, okay, and raise it to the x. And zoom 0. You got to make sure your my 6 intervals is in the window. So second function, calculate value after 6 intervals. 1.5, about 1.6 grams left. You agree with that? After 90 years. Right. So yeah, basically this is going to go. You start at 0, 100 grams. If you were doing this 1, you'd be down to 50 grams, and 1 interval is 15 years. So this would be 15 years later. 2 intervals, 30 years later, you still have 25 grams. Okay, that's 30 years later. Okay, and at 6 intervals or 90 years later, you have, what did I say? 1.6 grams still left. Okay, that's why pesticides are a concern. Okay, and I asked one of the farmers, it's still banned as a substance. Okay, that gives you a little bit, because I think some of you are going to go on into some science classes. Half-lives are one of the things you would study in chemistry. Okay, that's kind of 7.1. Now I want to give you about some examples in 7.2, okay, on exponential equations. The ones that we're going to do, we're only going to do 3 graphs, and those we're going to do with the calculator, just like we did on the examples. Okay, now this is exponential equation. An exponential equation is an equation in which variables occur as exponents. So you're going to have a variable up as an exponent. Okay? And for this assignment, I'll show you the main method. It will just say solve. An example, 4 to the 9n minus 2 power equals 256. What we're going to do on these is we're going to get the base the same. So you have to figure out 256 is 4 to what power? So on your calculator, you know 4 squared is 16, 4 to the third is 64, 4 to the fourth? Yep. Yep. So the key on these, Write a note out the side, star it, highlight it. Get the bases the same. And you always want to go to the smaller base, so like get it to base 4. Okay, if the bases are the same and there's an equal sign in between, then that means these two exponents are equal to each other. So set them equal. Set the exponents equal to each other and solve. So you get 9e equals 6, divide by 9, and reduce your fractions. N equals 2/3. Okay? And you can check those on your calculator if you substitute 2/3 back in. Okay? Everybody okay on that one? That's your answer. Number 2, 3 to the 5x power. You do have to make sure you can read your own handwriting. Make those as exponents. You have 3 and 9. Get it to the smaller base. This one would stay the same. 9, we can write that as 3 squared. And it's still to the 2x minus 1 power. When you raise a power to a power, what do you do with the exponents? Multiply them. So we'd have 3 to the 5x equals, we got to multiply this out, 3 to the 4x minus 2 power. The bases are the same. There's an equal sign in between, so set those exponents equal. If you want to, write a note outside, set the exponents equal. So you get the bases the same, set the exponents equal, solve. So you get x equals negative 2. Okay. Another example. 8 to the x minus 1 power equals 4 to the 2x power. I can't get 8 to a base 4. So I got to use base 2. 8 is 2 to the 3rd and raise that to the x minus 1. 4 is 2 squared to the 2x. Raise a power to a power, multiply the exponents. So I get 3x minus 3. Make sure you multiply both those out. Equals 2 to the 4x. The bases are the same. There's an equal sign in between, so set the exponents equal. Solve for x. I get negative 3 equals x. Okay. Okay, the last part is exponential inequalities. Only difference, they're going to use the less than, greater than symbols. Okay, if b is greater than 1, then b to the x is greater than b to the y. If and only if x is greater than y, and b to the x is less than b to the y, if and only if x is less than y. Okay, so if b is greater than 1, and this will make more sense with an example. Okay, if b is greater than 1, then b to the x is greater than b to the y, if and only if x is greater than y. And b to the x is less than b to the y, if and only if x is less than y. So they will say solve. Two to the x plus 2 power is greater than 1 over 32. You still get the base the same. 32, just 32, is 2 to what power?
3, no, 4. Five. It's 5.
2 to the 5th, right? Okay, so 32, so you have 1 over 2 to the 5th. If I move that up, what happens to the exponent? It'd be 2 to the x plus 2 is greater than 2 to the negative 5. Okay, if you move it up, it's going to make it a negative exponent. So now, if the 2 to the x plus 2 is greater, so you got to set x plus 2 has to be greater than negative 5. What do you have to remember about if you solve an inequality? If you multiply or divide by a negative, you reverse the arrow. Okay? So, on this one, we're just going to subtract 2. We're not multiplying or dividing. So, x is greater than negative 7. Okay? Everybody okay with that one? Okay, last type of example. They will ask you to write an exponential function for the graph that passes through, right, an exponential function for the graph that passes through the given points. Okay, so on this one, they're going to give you 2 ordered pairs, and they want to know what's the beginning, and it has to be an exponential function. So here's the 2 ordered pairs: 0, negative 2, and negative 2, negative 32. Okay, so you start with the y equals a, b, because they want an exponential function. They're giving you the x and the y. Okay, so start with this first ordered pair. The y is negative 2, the a we don't know, the b we don't know, and the x is 0. What's b to the 0 power? 1. So a is negative 2. Write that equation again. Y equals a b to the x. Now you know go with this one. The y is negative 32. Now we know what the a is. The a is negative 2. The b we don't know. And the x is negative 2. Divide by negative 2 on both sides. So you get 16 equals b to the negative 2. What's that negative 2 do to that x? What's that do? Be 1 over b to the second. Cross multiply. That's 16, same as 16 over 1. Cross multiply. So you'd have 16b squared equals 1. Divide by 16. B squared equals 1/16. Get rid of that. Take square root of both sides. So B equals, yeah, and they're considering the positive. B equals 1/4. I think that's all they're doing. You might look on the answers in the book. So B equals 1/4. You're not done. Now you go back and you write the equation. This is the 3rd time you write the equation. Y equals a b to the x. They want it in equation form, so you're going to keep the y and the x. What you have to put in is the a that you solved for was negative 2. The b that you solved for was 1/4. And raise it to the x power. Okay, now on your calculators, graph that. So graph negative 2. And then 1/4, you got to put that in parentheses, and raise it to the x. And do zoom 0. Now, test the ordered pairs. Do second function calculate value if x is 0. If x is 0, what's your y? Oh, good. Negative 2. So our equation's right. If x is negative 2, do second function calculate value at x equal negative 2. Whoop. Do you get negative 32? Negative 32.
Negative.
So this is the correct equation. So you actually write that equation out. To be able to work it, you got to write this equation out 3 times. Substitute in, okay, and solve for A and B. Okay?